Welcome back, everyone, and today we have another video related to more IK solvers. And in today's video, I'm going to illustrate how to build something. For a lack of a better word, I'm calling it a piston IK solver. It's kind of like an antenna, where you can kind of fold things into each other. It's telescopic, maybe, might be a good word for it too. But let's just for something simple, let's just call it a piston solver. So, as you can see on the screen right now, we're on our third solver already, and the third solver illustrates what I call a piston solver. What it does is really just fold in on itself. This is more of a mechanical, machiney type of thing. So if you have machines, they have like hydraulic things. You like things that are telescopic, and you want things to kind of fold into each other. This probably IK solver would be great for it. Or you can come up with other good uses for that type of solver. So we're going to figure out how this one works. And yeah, so I'll quickly go through some quick theory about how to go about it, and then we'll do some code. I'm not going to skip over like how the data is managed. That's done. I did a lot of that in the previous video because the previous video was an hour long. I had a lot to do that one. So I'm going to skip how data works, because just watch the previous video with the circle arc and you understand how the first part works and everything else and how that illustrates if you're new to this. If you're not, we're just going to continue on and hopefully make this video shorter than yesterday's video. So today we're going to do the piston solver. So that takes up too much resources, so I'm going to go this way. So the telescopic piston type of solver is pretty easy. We're not doing rotation. All we're doing is positioning. So what we have to do is change the position. So let's say I have my bone. That's bone 0, bone 2. And I'm purposely trying to make these uneven to illustrate a specific idea. All right, so here's an uneven bone, because we always have to make sure that our IK solvers works with variable bone lengths. So because a lot of times when like for me, when I'm writing these solvers, I do everything equal length. It works beautifully. I start doing odd lengths in there, and everything kind of just falls apart. So we always have to make sure that everything works with variable length bones. So let's say this is our IK chain. So this is fully extended. This is its complete length, and we want let's say our target to be here. So that's our target. That's the start of our chain. So that is the target length that we're trying to achieve with our inverse kinematics. So that's the length of our chain, and we need to fold this up to the point where this point can touch this point, which is a very simple solution where you take the maximum chain length subtracted by our target length, and we get this. This would be our, lack for a better word, this is probably what I call it in the code, remove length. This is how much remove length I need, okay? So if everything is even, I can just say remove length divided by 2 bones, and I just move the 2 bones by that. If the bones are uneven, you can't just divide by bone count minus 1. And you might be like, why am I doing bone? Why am I not dividing by 3 bones? You're dividing by 2 bones, because you have to. Because it's, first of all, the first bone can't move at all. So this is static. This is like if it's the leg, it's attached to the hip. It's not going to move the hip. It's not going to move into the hip. Same thing with the like at the shoulder. An arm is not going to shift it past the shoulder bone. So the origin is locked in place. It can't move. So everything else has to shift into it in this direction toward it in one straight line, because this is like a straight line kind of IK solver. And another thing you have to kind of realize is that the lengths of the actual bones themselves that need to move are not important. It's their parent length, because you got to remember everything is shifting into its parent. So this bone is going to shift into that bone. This bone is going to shift into this bone. So that one goes there, and this one goes there, right? And make a little eyebrows for the eyes. So when we're going through the code, we actually have to take this section into consideration, right? Because so we would need to move this amount of space, but we're moving it into this kind of space, okay? So this is the space we can need to move, because the bone 1 needs to go into bone 2 needs to go into bone 1, and bone 1 needs to go in bone 0. So we need to shift. So that is the space we have available to us for movement. But since everything is variable length, like we can't just divide by 2 because it'd be uneven. Because if we divide by 2, the smaller bone will shift too far into it, because there's not enough space to do it. So what you're going to do is you're going to add up the length of this part of the chain, basically all the entire chain minus the last bone. You just ignore the last bone when you want to do this. Like I said, the length of the last bone doesn't matter. It's every bone before the last bone counts. So you get the length of the moving, I guess let's call it M length, the moving length, how much space we have to actually move. And this is how much space we want. We take that and we say bone 0 length divided by M length, which would be this one, and then B1 length divided by M length, and that's this one. So what we're going to do is actually divide this. Basically, we're going to actually turn these values into a scalar value. So that's what we're doing. So we get the maximum, and then we use the individual pieces to make a scalar value. So the value will always be between 0 and 1. By having that scalar value, so once we're in bone 0, we need to move it into bone. When we're trying to move bone 1, we want to move it into bone 0. We say, well, how long is bone 0? It's that long, and that's the maximum length. This is where we get the ratio. So when we get that ratio, we then B0L M length multiply by RM length. So this equation actually gives us the amount of space we need to move. And then once with all that done, is that subtracts the bone 1 length. Yes? No. No, it's bone 0 length. No, it's bone. No, it's bone. I forgot what the code is. I think it's bone 0. Let me try to erase that. Because once we have the amount that we want to move, we need to subtract it from. It's actually the y position of this, so it'll be bone 1 y. So that y position subtracts by that amount of movement, because all the bones are set up in an up direction. So maybe if your bones are done in a different way, a different fashion, like if it's through an X position, X axis or the Z axis, you might just have to change the code to change it, or fix up the code where you can define which axis you want to change everything on your bone specifically. But my armature system, everything's built on the Y axis going up, so that's why I say just take the bone number 1. It's y minus this, and that gives us the new position of where this bone is in relation to its parent. So essentially, where you see this M length, we end up taking this space and we end up dividing it like that. So it's evenly divided. So this is the amount of space that this bone is going to move at, and this is the amount of space that bone is going to move at. So basically, like I said, we're trying to divide the amount of space that we're moving evenly, but in relation to the overall size of the bone of the space available. If that like that's what I'm trying to illustrate here. So I'm not just dividing by 2. I am dividing by 2, but in a scaled fashion. So like I said, bone 1 has more space to move, but bone 2 has less space to move. That's right. The stylus doesn't record. So this is bone 1. It needs to move into bone 0 space. So it has all this space to move at. And like I said, and this is bone 2, which moves into its parent, which is bone 1, and only has this amount of space, has less space to move in. So like I said, if that total amount of space has to be divided evenly amongst the actual scaling of that, and that's essentially the math. And that's all to it, really. Once you shift to everything, as long as you have that available enough space to move, then this point and the 2 points will then match up together, and you will have a perfect IK. Single pass, you have to do nothing else. There's other conditions you need to take in consideration. We have to look at the code, like what if the amount of space you want to move is so big that it's greater than any one bone? So we do a quick check to say, well, is the remove length greater than any bone that we have on the chain? If it is, we just automatically just collapse everything. Every bone will have a Y value of 0. Everything just gets collapsed. It won't be able to reach the target, but it tries to do its best job as it can by its available space. So, like I said, it's like a telescopic type of thing, like an antenna. Everything just collapsed to the bare minimum of space that's available, even though you can't reach its target. Same thing, you have to check if the remove length is like if the target. You have to check if the remove length is greater or I forget. It's like if the distance from the target is greater than the actual chain length, then have the entire chain completely extended. So you take the bind pose of your chain and just apply it to your thing. And we did this in the previous video where I go through the full direction function. So I'm not going to go through that. But overall, like I said, it's telescopic. You try to do the same thing as yesterday. Either you're going to fold everything into each other, or you're going to maximize everything. So it's just, that's all you're pretty much doing. Hopefully that didn't look dirty. So that is the theory behind the Piston IK solver and the math that I came up with to get it to work right. So we're going to go look here. And as you can see, I already have some code running. I don't need that one. All right, so I'm taking basically the exact same code from the previous video and just change it up a bit. Everything's kind of off the same way. We still have render. The code is almost identical, except just small little bits in here just to animate the piston itself, like a, yeah. So let's see. Let's not animate it yet. Let's deal with it actually as is. Okay, so the code is the same thing. We're dealing with the target. I explained it already, so I'm not going to go dive into targets again. So our main concern really is just our piston. So that's the only thing we need to worry about, because if you've seen the last 2 videos, everything else here is already pre-explained, like how IK chain poses works and IK target and everything else. So here we go. Here's piston. We're going to pass in the same thing I'm going to do for pretty much every IK solver. I pass in the chain, I pass in my target, and I pass in my pose where I'm going to save it to. So if the target scale is greater or close to 1 or greater than, I'm going to do the full direction. That's like full extension, maximum extension. And I have a priority set to true, so that means I want to reset its rotation and I want to reset its position. So I want to be maximized. If the scale is not known because I'm not animating by scale, that means I have like an end target in place. So I'm actually doing inverse kinematics. At this point, this one is not necessarily kinematics. This is me just animating. Here, I'm actually doing inverse kinematics. So this way I know my end point. So I need to know what my start point is. So this is when I calculate my end point, my start point. So this way I can then end up calculating my actual scale value, because the scale value helps me do certain things. And once like I said, this is the exact same code from the previous video. So, like I said, and I double check, because like I said, this is when I'm animating, and this is when I'm actually doing IK. Aim direction, I'm just aiming everything at the direction, and this property is turned true because I need to rotate the direction with an additional 90 degrees. Because like I said, the forward direction is this way, but I'm pointing up, so I need to do an extra rotation. So that's what the true. If you remember seeing the function from yesterday, I'm just adding the extra 90 rotation so to make sure the point of the bone is pointing in the forward direction. So just keep that in mind, that's one small little change from the previous code. But the code is all there. I just had it set to false before. Now it's set to true. Now we're going to go check compression. Like, do we compress it all the way? And this checks this. Like I said, this goes through all the chains and try to find if there's a bone that if there's a bone length that's greater than the actual target length. That means the target length is there's too much to take away. I don't have enough space. So I'm checking to see how much space I don't have enough space. So if I find one bone that is greater than the length of the target, then I say do compress. And if do compress does exist, you know what? I just see a nice way to optimize this. I didn't even think about it. I did this as like two separate if statements, and so silly of me. Like, I don't even need to compress. I can just do this. It's probably a bad idea to do this, but, you know, I don't want to give you guys bad code. I did this. I finished optimizing this function last night. It's like 2 or 3 in the morning. So I didn't even realize I can just do this. So, yeah, it's like I don't need to break. I just return. So this should work just fine. Now, this is now a lot more optimized. At this point, I don't need do compress. One less variable. So if I find one bone, that means that's it. I'm done. If I find one bone that's larger than the target length, I'm done. So at that point, I then set all its positions to 0 and tell it that's it. So like I compress everything down to its its parent's maximum length or minimum length, which is be 0. I don't want to go past it. I don't want to go in a negative direction. I want to keep everything at 0 or greater. If you want to change the rules for yours, where the bone can actually extend further in, that might make sense. I guess if you're doing like Wolverine claws or something, I don't know. Because sometimes, like the way Wolverine claws are drawn, sometimes they're like longer than the actual arm that they're in. So, whatever. It depends on the artist. Some artists draw the small claws, some draw them like massively long claws. I don't know why. It's unrealistic. But yeah, this little fix should optimize it one further, because one less if statement and one less variable I'm dealing with. Hope I didn't break this. Let me check. Okay, that's right, I turned off animation, but it looks like it's working. So that's compression. And the last bit of code is that part I said where we're going to divide everything evenly based on the scaling of the bone. So, like I said, I get the last index. I get the remove length by taking the chain's total length minus the target length, so we know what the difference is. So if I want to get the length so minus the last bone, so I take the total length minus the length of the last bone. So this way I have that total length available space, like this M length area. That's what I'm trying to get to here. And I divide by 1, or I have to divide over 1 because instead of doing a division, I can do multiplication. Because if I'm doing a loop and I have a lot of chains, I'm better off doing one division, a bunch of multiplications, than a bunch of divisions. Again, it's just optimization tricks for the CPU. I always keep reminding people about this in every video, just in case there's new people who don't realize that division is slower than multiplication. So we do that so I can just avoid division. And then we just go in. I just loop between 0 and before the last bone, so I don't access the last bone at all. I so this way I start from bone 0 and then work myself up to bone n-1. So I can get the parent's length. So this way, when I actually save the Y position, I'm actually saving to the child. So I'm actually going to use the parent's length. Like I said, I'm using the parent's length to do the scaling, then apply that to the child, because the child is actually to move into the parent. And this is how I go about doing it. I loop the parent, but I apply the values to the children, and that's why I do it less than the last index. So if I have 0, 1, 2, I just loop 0 and 1, because when I'm on 1, I'm going to apply the results to 2. So it's the next one over. And this is the equation, which is the parent's length minus the total length times the parent's length by this n-length inverse, which this creates the scalar value. That scalar value then multiplies by the length, which gives me that little chunk. Gives me which chunk, like over here, so I have this piece or this piece, and that piece minus the actual parent bone gives me how much space to actually move. And the end. And that's it. Oops. And that should do it. So that's the end target. Everything's kind of compressed a little bit in, so you can kind of see that in this bone system, everything's compressed just a little bit. If I go into my tentacle rig and add this, I can, like I said, now we have to really check to see if it works with variables, and I know it does. So if I click refresh, and the change I did, in case you haven't realized it, I take the bone length, I add the increment times 3. So every bone, so the first bone is the actual bone value I set, so maybe it's like 0.3. The next bone is going to be 0.6, and the next bone is 0.9. So every bone I create down the chain gets bigger and bigger. And so the final bone is the longest, so it has the most amount to travel. But there you go. Everything still kind of just folds in. Like, even though the bones are now uneven, everything kind of just folds in correctly. And like I said, I can go here and just animate it. Move the target. And there you go. So even though bones are uneven, here's the target. I'm moving the target, but it knows that the largest bone is the first bone. It just compresses everything. So it just, instead of doing all that math, it just saves some processing time when we know we can't do it. So there you go. And that's it. That is the Piston IK solver. Like I said, it's good for mechanical things. And yeah, there you go. And that ends up creating, and like this example, the bones are even. But like I said, it passes both tests. Does it work on even bones, and does it work on uneven bones? And like everything, I always have to test it. So it's always important to test. So yeah, there is the third IK solver for our IK chain system. Now I'm going to record the next video, which is going to be a 3-bone solver, which would be for like animal legs and whatnot. So yeah, so I guess I'll end it at here. Last night I got another Patreon. It's like, wow, thank you very much. Look, I'm up like at 1 or 2 in the morning, and I got an alert. I said thank you right away. So again, in the video, I want to say thank you very much. I definitely appreciate you. I'm getting more Patreons now, and every single one of you, I try to now respond to you and say thank you, because I do really appreciate it. Every dollar counts. So yeah. Please like and subscribe, and we'll see you in the next video, which is probably be more fun, because that's the animal leg IK. This is kind of simple and probably boring, but it has its uses. And if Ubisoft went out of the way to show it, I went out of my way to try to make it. Because if Ubisoft has it for some reason, it might be good to have it around. So here's the good working example of what it is. I just wish I had a better name for it. If you guys have a better name for it, maybe I'll change it from Piston Solver to, I don't know. I don't want to call it telescopic. I just think it's a long name. Piston sounds easier, just Piston. But yeah, so I'll end it like that because I got 25 minutes. So I'll try to keep this video short because it's not worth making it long. So the usual BS, like and subscribe. I'll see you guys in the next video, which I'm going to start recording in a minute. See ya.